This video is about characterizing silver-silver chloride electrodes using impedance spectroscopy. It corresponds to section 39.5.4 of the Applied Analog Electronics textbook. Now, the setup is almost identical to the setup we used for the stainless steel electrodes. We have a pair of clip leads attaching the electrodes to here I'm using the Analog Discovery Impedance Analyzer board. You'll probably be doing it with a breadboard where you've got the device under test, the pair of electrodes, and a resistor in series. And you'll have to choose that resistor to get the appropriate values for the impedance. So you want the resistance to be similar to the impedance you're measuring. The solution here is the same 35 gram per liter solution that I used for testing the stainless steel electrodes. You'll again want to be doing this with all four of your different concentration solutions. Incidentally, when you're doing different concentration solutions, it's good to start with the lowest concentration first, so that after you've made that measurement and you move the electrodes to a higher concentration, the tiny amount of liquid that's still left on the electrodes is not going to greatly change the concentration of your solution. If you start with the highest concentration solution, then the salt that's in that's left on the electrodes as you move it to a lower concentration will actually increase the concentration of salt in your reagent. You'll be contaminating the solution each time you do a transfer. Here I'm just doing one test with a fairly high concentration. It's not the same bath that I did the electroplating in. That electroplating bath is basically contaminated. You can't really use that for doing measurements. Okay, so I've got this thing, I've got it set up using the lines on the electrode holder to immerse to a constant depth, so that I don't have this thing sort of at a random depth, but I have it always to exactly the same depth. You want that so that the only thing that's changing as you change solutions is what the solution is, and not how much electrode you have in the solution, because the area of the electrodes in the solution will affect the measurements you make, and that could get confused with what you're really trying to measure, which is the conductivity of the solution. Okay, so let's go over to waveforms, and we'll need the impedance analyzer. And just like we did for stainless steel ones, we'll start with an arbitrary resistance here and just do a single run at high frequency to see about what sort of resistances we're dealing with. And this is looking like this is only an ohm or two. I'm not going to want to use a 1 kilo ohm sense resistor. Let's try switching that down to the 10 ohm sense resistor and see if all right, that gives us a more constant measurement. Oh, and we're still looking, I want magnitude of impedance, not real and imaginary part. Okay, so there's still a little bit of what looks like inductance here at the high end. We want to do compensation, but we're looking at pretty low resistances here. So let's start by doing the open compensation. I will disconnect one of the clip leads and perform, before I perform open compensation, let's pick the frequency range you want to do. I think I want to go all the way from 10 hertz up to 10 megahertz, and 30 samples per decade will probably be enough. All right, so I still have the wire off, so I can do the open compensation now. And the first couple of measurements here where you've got very low frequencies are quite slow. And because our sense resistor is only 10 ohms, our noise level here is at about 1 mega ohm. or actually down to 100 kilo ohms. And that's because the voltage across the 10 ohm resistor is very small, and you get discretization noise. You can save this if you want to save the compensation information. We can now clip both to the same electrode and perform the short compensation. And the short compensation here, it's looking like things are around 150 or 180 milliohms, something like that. But there is quite a bit of inductance. All right, and now we can turn on both the compensations and hook this thing up so that we have each clip lead on its own wire, and do a run. And we're seeing about, what is that, 13 ohms? I could use the little cursor here, I guess, to take a look. It's about 11.6 ohms. It does drop a bit with frequency, but not very much. And it does go up a little bit here at the end. And again, that's probably because there is actually a little bit of inductance there. We're seeing fairly small changes. It's not purely resistive. If we look down at the phase here, we can see that we had like a -5-degree phase, which is not purely resistive. There's a little bit of capacitive component. And then we can see that here, a little bit of downward slope. Not clear what the best way to model this one is going to be. This region in here is pretty flat, and the resistance is, the phase is near zero, so that region might be best modeled as a resistor, perhaps with a small capacitive-like component here. Or you could just say, hey, this fluctuation here, we're looking at a difference between 11.6 ohms or something and 9.3 ohms. You could just say, hey, it's 10 or 11 ohms flat across the whole thing. So different ways to model this depending on what you think is important in the behavior of this electrode. So save this and repeat the experiment, each time going to a higher concentration of salt water. Since this was a fairly high concentration I was working with here, you might not see these 10 or 11 ohm values when you're working with the low concentrations when you start. So do a quick sweep initially to figure out whether the resistor you're starting with works. Change the resistor if you need a smaller or larger resistor to be in the same ballpark as the impedances you're measuring. And have fun measuring your silver chloride electrodes. When you're done with all of these, you can take a pair of your EKG electrodes, put them face to face, and put a clip lead on either side of that to measure silver chloride electrodes as well.